Welcome to this module. This module is a continuation of our last module, in which we were looking at the op-amp data sheet, and then we were looking at the characteristics of op-amp, and we have seen what is input bias current and how we can remove the effect of input bias current on the output. This module we will see what exactly is an input offset current and how does input offset current affects the amplifier operation. Right. Now, we already have seen what is input offset current, we have seen in the earlier lectures. The formula also now we know very well. The formula of input offset current is nothing but IO1 or IB1 minus IB2 mode of IB1 minus IB2, right. Input bias current was IB1 plus IB2 by 2. Input offset current is IB1 mode of IB1 minus IB2. Right. So, now let us see how this is going to affect the amplifier operation. So, if I see the slide, what can I find? I find that input offset current definition, which we already know, right. Then I see that the input offset current for typical 741 is 200 nanoampere maximum. As the matching between in two input terminals is improved, the difference between IB1 and IB2 becomes smaller, that is the input offset current value decreases further, correct. So, for a precision op-amp 741, input offset current is nothing but 6 nanoamperes. Okay. So, input offset current is nothing but 6 nanoamperes for a precision op-amp. To understand the effect of offset current on the op-amp, let us consider an inverting configuration as shown in this particular figure. So, what we find, there is a R1, there is R2 inverting op-amp, and then we have R3, which we already know, which should be equal to R2 parallel to R1. Now, if I apply Kirchhoff current law at node A here, I1 will be nothing but I1 equals to I2 plus IB1, right. So, applying virtual ground, I will have V in equals to V plus equals to minus IB plus, right. IB plus will go here, IB plus, here will be IB minus, right. Here will be I1, I2, right. So, V minus, which is voltage over here, right. So, V minus will be equal to V plus equals to minus IB plus, right, into R3 into R3. Right. So, from Kirchhoff current law, I1 is nothing but I1 is IB plus, right. I1 would be nothing but IB plus into R3 by R1 into R3 by R1, and I2 would be nothing but minus IB plus into R3 minus VO divided by R2, correct. Now, if we on substituting the values, we will have IB plus into R3 by R1 equals to minus of IB plus into R3 by R2 minus VO by R2 plus IB minus. So, if I solve this equation further, what I will have, VO will be equal to R2 into IIO, right. Now, a typical offset current of an op-amp is 200 nanoampere. It results that with an op-amp has a feedback resistance of 1 megohm, the op-amp would produce an output voltage of 200 into 1, which is 200 milliampere for 0 input offset voltage. This much is the change, some 200 millivolts, right, that is generated at the output voltage, and the value may be too high for many circuits, right. So, on the way to minimize this is by keeping the feedback resistance small. Unfortunately, to obtain high input impedance, R1 must be kept large, right. R1 should be large, otherwise we will not have high input impedance, and we know that in op-amp we should have extremely high input impedance. So, we cannot do that. Now, feedback resistor R2 must also be high, otherwise we cannot have gain, same problem, right. The idea is, if I can reduce value of R1, or if I can reduce the value of R2, then I have a minimum effect, but I cannot reduce the value of R2, and that is why I do not have any solution till this point. Now, let us see. So, if I want to compensate the effect of due to the offset current, what should I do? Then the feedback network, right, here you can see here it looks like a T, right, it looks like a T, that is why we say T feedback network shown in the figure is a good solution. How? How is a good solution? Let us see. This will allow large feedback resistance while keeping the resistance to the ground. See by inverting input low S shown in the dotted network. So, if I have RT plus 2 RS, RT plus 2 RS, RT and RT, and here will be my RS, this configuration will help to compensate the effect of the offset current. So, by T 2 pi what we have, RF is nothing but RT square, right, RT square plus 2 times RT RS divided by RS. So, to design a T network, first let us speak RT less than RF by 2. Okay. So, first what we should do? We should pick a value of RT which is extremely less compared to RF by 2, then calculate RS. So, RS would be nothing but RT square divided by RF minus 2 RT, right. Now, if there is a value, then I can have value of RS and I can value of RT. So, two things we have to know from these equations, right, that we can design a circuit that can be used as a good compensation circuit for the effect to remove the effect of the offset current, and how we can choose the value of RT and how we can choose the value of RS. Now, let us take an example. Let us take an example. Design an inverting amplifier of the type shown in figure using 741 to get a gain of minus 10 and input impedance of 10 mega ohms, right. Also calculate RT, RS and R1. This is the problem. So, let us see the solution. Since what we is that gain is nothing but minus RF by R1, we have RF equals to gain into R1. This CL should be a subscript. So, we can say RF is nothing but gain into R1. So, we have RF value 100 mega ohms. Now, let RT be 47 mega ohms, right, because we know that R2 is nothing but, if you see last slide, RT is less than RF by 2, right. So, RF by 2 is 50 mega ohm, we have less than 50 mega ohm, let us very less than 50 mega ohm, let us say RT equals to 47 kilo. For that our RS value would be nothing but 22 ohms, RF will be nothing but 22 ohms, right. Now, let us see another point, that is we have to understand the effect of input offset voltage on the amplifier operation. We will see now effect of input offset voltage on the amplifier operation. So, what is the input offset voltage? We already know, right. Another practical concern of op-amp is voltage offset. Even though the effect due to offset current and bias current are compensated, the output of op-amp may not be still 0. This is due to unavoidable imbalances inside the op-amp, that is the effect of having the output voltage something other than 0 volts when two input terminals are shorted together, right. So, we have seen what is input offset voltage earlier also. Let us see, remember that op-amp have differential amplifier, they are supposed to amplify the difference in voltage between two input connections and nothing more. When the output input voltage difference is exactly 0 volts, we would ideally expect output to be 0, right. However, in the real world this rarely happens, even if the op-amp in question has 0 common mode gain, the output voltage may not be 0. This deviation is nothing but your offset. This deviation is your offset. A perfect op-amp would exactly have 0 volts where both inputs are shorted, right, like here when both inputs are shorted the output should be 0 volt, right. But most op-amps of the self will drive their outputs to saturated level either negative or positive, right. For example, in the given figure what we see, the output voltage saturated at value 14.7 volts, just a bit less than plus 15 volts. So, the reason is this is because the offset in the op-amp is driving the output to a completely saturated point. It is very difficult to estimate the amount of offset present at the output, right. Now, how to compensate then this effect of offset voltage? Very important point, very important. Okay. So, these are all the important points that we are discussing, because it is very important that we compensate the effect of offset voltage, we compensate the effect of input bias current, we compensate the effect of input offset current, so that when the terminals are grounded our output should be 0. That is how we have offset, our offset should be perfect such that our output voltage should be 0, it should be null, right. So understanding these parameters, understanding these characteristics would help us to design the amplifier accordingly, right. Now if we go back to the slide, what we see that how we can compensate the effect of offset voltage. To do that, one way to compensate for the effect due to the offset voltage is by applying small voltage in series, with one of the inputs to force the output voltage to become 0, right. This is one way of offsetting the voltage. Being that op amp differential gains are high, the figure input offset voltage does not have to be much effect on the output even the inputs are shorted. Right. Since the differential gain is very high, the effect of the input offset voltage is not really going to affect our output. There are usually provisions made by manufacturer to trim the offset of the packaged op amp. How? Usually 2 extra terminals of the op amp package are reserved for connecting external trim potentiometer. These connection points are labeled as offset null. So, if you have seen the IC, the terminal 1 and 5 are used for offset null, right. For a single op amp such as 741, the effect of null connection points 1 and 5 like on the 8 pin DIP package are used for offset null. So, we connect a potentiometer between 1 and 5 and we trim the voltage, right, trim the potentiometer such that our output voltage would be 0. So, let us see an example for op amp characteristics. We are looking at an example. For first is for the non-inverting amplifier shown in figure, this one, R1 is 1 kilo ohm, RF equals to 10 kilo ohm, calculate the maximum output offset voltage due to VOS and IB. The op amp is LM307 where VOS is 10 millivolts and IB is 300 nanoampere, IIO is 50 nanoampere, right. So, first thing is we have to calculate the maximum offset voltage. The maximum offset voltage VOT is nothing but 1 plus RF by R1 into RF into IB, right. This is RF into IB. Okay. So, if I substitute the value 1 plus 10 by 1 into 10 milliampere, right, 10 this is 10, right. Okay. So, it is a 10 millivolts plus 10 kilo ohms, right, because RF, this is VOS, right, VOS here, this is RF, this is R1 and here we have again RF and then we have IB. What is IB? IB is nothing but 300 nanoamperes. So, what will be my answer? My answer would be 113 millivolts. Very easy, we just substitute the values of RF, IB, RF and R1 to obtain the value of VOT. Let us see the second problem. Second problem is calculate the R comp needed to reduce the effect of IB. So, the value of R comp needed is R compensation is 1 K parallel to 10 K. We have known, right. If I want to have R compensation, resistor R3 would be R in parallel to RF. So, 1 K parallel to RF is nothing but 990 ohms. Third thing, with R compensation in circuit, what we have VOT. So, calculate the maximum output offset voltage if R compensation is calculated in B, right, is connected in the circuit. So, assume that R compensation is connected in the circuit. Now, we calculate the VOT. So, in this case we have 1 plus RF by R1 VOS plus RF RI into IO. So, we will have 1 plus RF by R1 into VOS, right, which is this value plus RF into IIO which is this value. So, our output voltage VOT would be 110.5 millivolts. So, it can be seen from this example that it is the input offset voltage which is more responsible, right, input offset voltage which is more responsible for producing an offset voltage compared to input bias current IB, right. So, you can see that what is the more responsible for the output for producing the output offset voltage. Input bias current is what? What is input bias current and what is input offset voltage and what is output offset voltage? From this example what we have seen? We have seen that that it is the input offset voltage which is more responsible for producing the output offset voltage rather than the input bias current, right. So, when you see a problem you understand that what is the role of this problem and how you can what are the parameters that are responsible for the result, for the final result that we are desiring for, right. In this case what our desired thing is that the output should be at 0 when we are grounding both the input terminal, that is only one thing that we want to understand, right. Now, we will see few more characteristics of op amp in the next module. Until here what we have seen is what is the role of the input offset voltage, how we can compensate input offset voltage and how we can compensate the input offset current. In the next module, which is the last module of this particular lecture, we will see few further characteristics of op amp that are already mentioned in the data sheet. Alright. Till then you take care, I will see you in the next module.